And just continuing in yesterday's notes, today we're going to talk about the factors affecting rates. And this is going to kind of carry over the next couple of days. But the first factor that affects rates is reactant concentration. And really what we're going to see is the more reactant we have, which is why we talked about molarity. All right, here's our molarity sign again. The more we have, the quicker things can react. All right, and we talk about this really in terms of the rate law. And you'll see here shortly that we have an equation, what the rate law is. There's a rate constant, and we talk about concentrations of reactants. All right, so here's just an example equation. We're going to have little a moles of capital A plus little b moles of B yield some sort of products. All right, where A and B are our coefficients, so there's some whole number, all right, from a balanced equation. And A and B, capital A and capital B, are just some reactants. So the rate law always kind of looks something kind of like this. The rate of our reaction is approximately, that's what that little funky alpha sign is, it's approximately equal to the concentration of A times the concentration of B. And notice here that rate only depends on reactants. There's nothing to do with products. It is strictly dependent on what we start with. Typically the way you're going to see rate, and the way it's going to be on any kind of test, and it's the way it's in your book, is really rate is not approximately equal to something, but we can say it's equal to something exactly. And what rate is equal to is K times the concentration of A raised to some power times the concentration of B raised to some other power. And we're symbolizing this with M and N. And notice that they aren't the same letter. So again, M and N are going to indicate the sensitivity. Okay, so M and N, they are how we are raising our concentrations. M and N indicate the sensitivity to the change in concentration of A or B. Okay, so how is the rate affected by either A, or how is it affected by B? And again, they are two separate letters, so they mean two separate numbers. And these are always determined experimentally. All right, it's important, it's in red, always determined experimentally. Notice this is lowercase m and n. It is not lowercase a and b, so it has nothing to do with our coefficients from our balanced equation. Alright, k, lowercase k, is what's known as the rate constant. And the rate constant, you might jot this in your notes, is constant for any given temperature. If the temperature changes, the rate constant will be different. But for a given reaction at a given temperature, the rate constant is just that. It is constant. When we kind of go back and look at M and N, alright, how we kind of what we're raising our concentrations to. If our exponent is 0, so if M or N is 0, it is independent of the concentration of A or the concentration of B. Okay? But 0 means independent of concentration. If we change our concentration, there's no rate change. Okay? If the coefficient is if the exponent is a 1, so if M or N equals 1, it is a direct relationship. And if we were to change our concentration by 2, so if we doubled our concentration, our rate would double. Okay, so 2 times concentration equals a 2 times change in rate. A negative exponent, so negative 1, is an indirect relationship. So negative 1 is an indirect relationship. So that if we doubled our concentration of A, our rate would actually be halved. Two, so if the exponent's 2, it's yet again a direct relationship. And this time, if we double our concentration, our rate is not only doubled, and in this case with 2 it is, but it would be 2 raised to the second power. Or in actuality, it would be 4 times the rate. Likewise, you might jot in your notes, 3 would be a direct relationship. A doubling of the concentration would be 2 raised to the third power, or 8 times the rate. Okay? Reaction order is the next thing we're going to talk about. So reaction order. We have the following rate law. We're going to write rate equals K, our rate constant again, times the concentration of A to the second power times the concentration of B to the first power. Okay? And again, these numbers 2 and 1 have been determined experimentally. And a couple things we can note about this. Our concentration of A is said to be second order. So order of A is second. Order of B is first. Okay? And then overall, we're going to add these orders together. So the overall order is going to be third. Alright, so individual concentrations, first order, second order, third order, and then to get our overall order for our reaction, we would just add up the individual concentrations to get the overall order. The next thing you're going to do in your notes, or actually we're going to, real quick before we get to the graph, letter C, determining the rate law experimentally. Determining rate law experimentally. So next week, or really our second big lab of the year, you will have an equation which we're going to determine concentrations experimentally, but this is generally the way the questions look. You'll be given an equation. In this case, we have 2 moles of nitrogen monoxide plus oxygen react to form 2 moles of nitrogen dioxide. And we can initially write our rate as being rate equals K times NO, concentration of NO raised to some value, times the concentration of oxygen raised to some value. And again, we're just going to write M and N here. If you can then jot this graph, or this table in your notes.
I just need the flashlight.
And I will give you a second to write this down, or just pause the video if you need to. But for experiments, we're going to run 3 experiments, and the concentration of NO for our first experiment is going to be 0.015 molar. And for oxygen, it's going to be 0.015. So concentrations are identical. And our rate is 0.024 molars per second. For experiment 2, our concentration of NO is going to be 0.030, so it's doubled. And our concentration of oxygen is going to remain the same. And our rate is going to change to 0.096. And then lastly, for our third experiment, NO is going to match the first experiment, so it's going to go back to 0.015. And we're going to double the concentration of oxygen, so 0.030. And our rate we're going to find is 0.048 molars per second. Alright, so really our step here is we're going to look at 2 of the 3 experiments. It doesn't matter which 2 we look at, but we're going to look at experiments 1 and 2 initially. And what is changing in 1 and 2? Well, we can see oxygen is not changing. Its concentration is the same. So our rate change is due to the change in concentration of NO. It has nothing to do with concentration of O2 because it's not changing. It's a constant. If you go back to experimental method, it's remaining the same, so we can isolate what does change in concentration of NO do. Alright, so we doubled our concentration of NO. And what did that do to our rate? Well, if we take 0.096 and divide it by 0.024, we're going to see that that's 4 times the rate. So 2 raised to what power equals 4? And so 2 raised to m equals 4. So what is m? M must be 2, or we're going to say that our order of NO is second order. Alright, so we have identified the order of NO, but we need to still find the order of oxygen. So if we compare experiments 1 and 3, in this case, NO is staying the same, so it's constant. So our rate change is not due to NO, but it must be due to oxygen. And we doubled oxygen, so 2 times the concentration of oxygen. And we're going to look at our rates, and 0.048 divided by 0.024 is twice the rate. So again, in this case, 2 raised to n equals 2. So what must n be? N equals 1. So oxygen is first order, while nitrogen monoxide is second order. So now our rate law can be more properly written as rate equals K times NO to the second times O2 to the first. So if we want to find K, we're going to substitute in, we're going to choose any of those experiments because K is a constant, so it doesn't matter which of the experiments we choose, but we're going to choose experiment 1, and we're going to substitute values into our rate law. So our rate was 0.024 molars per second, and that equals K, which is our rate constant, times our concentration of NO squared times our concentration of O2. And I'm going to put our units in here. So concentration of NO, 0.015 molar squared, times 0.015 molar to the first. And for now, I would appreciate if you put a first there. You won't see it in books or anything, but if you would put it there, I know that it's supposed to be a 1. Instead of you left it blank because you didn't know what number it should be. Alright, now we're just going to basically plug and chug. I know mathematically this is not a problem, but I would like you to see what happens with units, because our units for K change depending on which rate we're talking about. Alright, so here's our calculator. So we take 0.015 times 0.015 times 0.015. We get a value of 0.000. Let's see. 0.03375, and that's molars cube, or cubic molars, which is a really weird thing to say. Okay, and all that's times K. So how do we get K by itself? We're going to divide both sides by 0.000003375, and we're going to get this value, 7111. And our units are going to be 1 over molar squared seconds. And this is the unit for any third order reaction. And again, if we look at our order, our overall reaction is third because we have a first and a second, so that adds up to third. And kind of our rate on the left always has to equal molars per second. So K is going to change depending on really how many molars we are finding the product of on the right. So again, rate is constant. Rate is constant for a given temperature, which I mentioned above. So it doesn't matter which experiment we choose. But if the temperature changes, each of those rates is going to change. A question I might ask is, if temperature goes up, what's going to happen to the rates? Will they increase or decrease? You might put your answer in your summary today, but I'm not going to tell you right now. And generally, we say that values given in the book will generally always be at 25 degrees Celsius. All right, so units. Because units are always changing for K, if we have a reaction that is, let's say, third order, like the one we just did, the units of a third order reaction for K will always be 1 over molar squared seconds. For a second order reaction, they will always be 1 over molar seconds. Okay? And notice for a third order reaction, it has 2 molars in the denominator. For a second order reaction, it has 1 molar in the denominator. A first order reaction has the units of 1 over seconds, or just per seconds. And again, notice a first order reaction has 0 molar in the denominator. So the number in the denominator is always 1 less than the order of the reaction. A 0 order reaction, okay, so all of our concentrations go to 1, because anything raised to 0 is 1. So really the units of our rate constant K need to match the units of our rate, which is molars per second. So now our molarity just is in the numerator instead of in the denominator. If we had some sort of funky 7th order reaction, our units would be 1 over molars to the 6th seconds. But that is the end of podcast 2.2. Again, don't forget to do your summary, and feel free to ask or answer what would happen if the temperature goes up to the rate.